All right, hello everyone. We are with the Gore group, and our project was on modeling filtration with multiple layers. So the problem statement we were given was to develop an efficient and reliable network model for a multi-layer membrane to study particle filtration. In addition, we added to this to develop a continuum model for the framework for characterizing mass transport of species inside of a multi-layer porous medium, where the main focus is on the transition between layers and how that affects the efficiency of the filter. So our approach to solve this problem is to split it up into three different categories here. The first category is the discrete or network model. Then we move to a semi-discrete or a branch model, and we're also going to consider a continuous PDE model. So starting with the network model, we began with the one-layer model taken from the MPI 2009 report, where they end up solving a network that looks like this, where we have a source node where particles are inserted into the filter. They travel down through the filter in a certain way, and they end up at a sink. And this is done for a single layer. So what we do is, in this, once you're given the graph, you can determine the incident matrix, which is given like this, where a -1 determines that the edge is moving away from the node, and a +1 is moving towards the node. We then apply the Hagen-Poiseuille law, which ends up giving us these equations here, where P is the pressure on the node, and the Q's are the fluxes. So solving this system, we can determine the pressures of the interior nodes and then get the fluxes for the source and the sink. All right, so once we do that, we need to determine how the particle moves. So we define a probability of which edge the particle will travel down, and it's given by the ratio of the outward flux moving from node J to K along an edge I for an outward flux. And for an inward flux, probability is going to be 0, because the particle is not going to want to go in that direction. Then we also assign a pore size distribution based on this gamma distribution here. Finally, we apply a clogging condition. If the diameter of the particle is less than the diameter of the pore, the particle is going to pass through the pore. Conversely, if the diameter of the particle is greater than the pore will get clogged. And then if that condition is met, we then set the diameter of the pore to be 0, so no more particles can travel through that pore. Okay, so we do this for the single layer model, and these are the graphs that we get. The top two here are for a fixed particle diameter, where we see here is the retention ratio. Now recall that the retention ratio is the number of particles that have been stopped divided by how many particles have been put in. And because it's a fixed size, we should expect that this retention ratio would go down to 0, because at some point, all of the pores that are of a smaller size than the particle will get filled up, and then more particles will just pass through, and that should send it to 0. So this is what we see. And this is the relative flux, which should level out at some point after everything's been clogged up. Or the pores that are going to be clogged get clogged. These bottom two here are where we have a particle distribution on their diameters, and we see here the relative flux goes down to 0 as the entire filter gets clogged, and then the retention goes down to at some point and then starts coming back up. So this is what we would expect. So then we move from a single layer model to a multi-layer model. Now here we had two choices. The one choice is a locally distributed model of where we're looking at the interface between layers. So locally distributed, so this is layer 1 up here, and a node from layer 1 can go down to 2 nodes at the second layer. So this is, we call this a local model because it's locally distributed here. We also have the global model where all the nodes from the top layer can go down to a single node and then be redistributed to the second layer. So we consider these two models. So in comparing these two models, the global network is kind of nice because you can solve for that single node in between layers and then solve each layer independently. So that's what these equations are describing here. And then these two graphs show the flux and the retention for the local and global model when the diameter of the particles are fixed. And we see that there's a very close relationship that holds there. However, if we go to the variable particle diameter, we see that our flux here looks good, but there is variation in the retention. And we don't quite really understand what's going on in this graph right now. Okay, one of the questions that we had was looking at the difference between the arithmetic and geometric mean for the gamma distributions. And there was a question of whether that determines how well we can resolve this interface layer, and it looks like it does not. So that shouldn't really matter. Okay, so here we have plots for the two-layer local model. Right, and we see exactly what we would expect, right? So here we have the fixed particles sizes and the distribution of particle sizes, and they are what we expect. Similarly, we can do this for 3 layers. The model that we developed was for an arbitrary number of layers. So these are just the examples for 1, 2, and 3 layered cases. But it can be developed for any number of layers. Okay. Similarly, we can take this model and simulate exactly what one particle does once you insert it. And this is what this is describing. This is a network for 3 different layers. Right, here's one layer. You can see the interface. And here's the interface for the 3rd layer. This is the source. So a particle is going to get inserted here, and it's going to travel down to the sink. These red edges are where a particle got plugged up, or where a pore got plugged up. Okay, similarly, yes?
How are the axes labeled?
The question was, how are the axes labeled? The axes don't matter because it's just a network. So you could rotate this or flip it. You can do whatever you want to it. So the axes don't, there's nothing on the axes.
So which point corresponds to the input and which point corresponds to the output of the whole point?
Right, so the question was, which point corresponds to the input and which point corresponds to the output. The source node is right here, and the sink node is out here. So you're going to import a particle here. You're going to watch it travel from node to node along the network and end at the sink. Okay. All right, so then we went from our 2D local network model, and we're able to develop the same thing for 3 dimensions. So here we have the graphs for the 3-dimensional network model for the variable particle case, or I'm sorry, the fixed particle case and the variable particle case. Okay, so in conclusion, right, we set up a multi-layer lattice from the MPI 2009 code. It simulates particle behavior passing through multi-layers with different porosities for local and global networks. The model can handle any distribution of particle sizes and pore sizes. And then an extension was developed for the 3-dimensional network model. All right, so that concludes the network model, and we're going to move to the continuum models.
Before I start, I just want to say if there's anything wrong, because just hold on, ask at the end, because I'm going to say a lot of things possibly wrong on this time. So for the continuum model, we actually have 4 subgroups working on this. The first group worked on a branch model. So this is basically the structure of the branch model. A little bit of information to this. So during the filtration, we're going to have the filter become fouled by 3 different mechanisms. Adsorption is basically the small particle gets stuck on the wall of the membrane of the pore. Blocking is simply we have a large particle stuck on top of the pore. And a cave formation, which is something that we don't really consider in this in our project, which looks something like that. Then, so for the project, the geometry is simply planned in the YZ directions, and we have the structure vary with depth. So basically, on the first layer, in this picture, on the first layer you have 1 pore, and on the next layer you have 2 pore, and as you go down, the pore number increases by 2 each time. And yep. So Cij, Aij, and Pij represent the concentration of particles, the radius, and the pressures with respect to the ith layer and the jth column. So the governing equation for the velocity follow the Poiseuille's equations, which basically mean it is proportional to the difference in pressures, inversely proportional to the viscosity of the fluid, the length the height of the filter and of the pore, and the resistance, which is defined as these terms here. We also have a flux balance assumption. Which simply means that when the flux goes down this way, then it also the flux here are equal to the flux here and here combined together. And in the end, we have we have the same number of unknowns as the same number of equations, so we can solve this systems. So for the yes. So next we use the advection equation for the particle, which is this equation here, and we also because the pore radius decreases proportional to the number of the concentrations. So the more concentration particle at that pore, the faster the radius decreases. So we have these terms where that gamma is basically the attraction between the particle and wall based on the chemistry of the pore material, and alpha is just some constant that relates with the size of the particle. So we want to calculate the also the resistance due to the particle blocking, which is the large particle block on top of the pore. Then we define when a pore is open as 1 and when it's closed to be 0. So when it's blocked to be 0, we construct a state space. So basically, when m is equal to 2, you have 2 layers. The first layer has 1 pore, and the second one has 2 pores. And in this case, we have a total of 3 pores, and the state space look like that, where 1, 1, 1 correspond to all 3 pores are open, and 0, 0 correspond to all 3 pores are closed. So in order to know the total resistance due to blocking, we have this formula here, which basically looks like the expectation value of formula in probability. And so PK is just the probability of the state of the system being in state K at which is one of those at time t, and RK is the resistance added due to the big particle block on top of the system. And yes, so this is just a continuous time markup chain. So we want to calculate in order to calculate the total blockage resistance due to blocking. Then we want to know what RK and PK is. RK can be calculated from previously, which is actually calculated similar to the way you calculate a resistor in a circuit. And PK is this is sort of a way to calculate the PK. So you assume that, so for the case where there's 2 layers, you have 2 particle size, and you assume that the first particle has radius larger than the larger pore radius, and the second particle has radius smaller than the larger pore radius, but larger than the smaller pore radius. And the arrival times follow a Poisson process with intensity gamma 1 and gamma 2, respectively. So using some property of continuous time markup chain, you have this equation which relates this Q infinitesimal generator to P. And Q is a constant, so we can solve for P. So in the end, we have the R adsorption rate and R blocking, and we just add them together to get the total resistance of the whole systems. Then we do some simulation with what we have, and So this here represent the same initial resistance in both figures. The first figure has the flux and the throughput through three cases. The first case go from two membrane to four layers, to four layers. And the second is just the particle concentration and the throughput. The throughput is defined as the total fluid being filtered from the beginning until the filter gets stuck and get clogged. And as we can see that the throughput increases with more layers when we have more layers in our filter. And over here we have the particle concentration at outlet is basically the percentage of particles get to survive until the end of the filter. So for four layers, we have about roughly a little bit over 2%, and that means that more layers is better for a filter. Then we also simulate for a fixed case of 4 layers. We vary the additional resistance and the Poisson's parameters. So when in this figure, you have the fixed case is the reference case is when rho equals 0.5, which is this bottom line here, and we have this case when rho equals 0 is over here. So yes, with respect to yeah, and this is I find this more bit more interesting. So this basically saying that when we have more large particles coming through the filter, then we have then the filter is producing more then we have more total fluid getting filtered, which is a little bit counterintuitive, but it's actually due to a leakage. When you have a large particle blocking on top of the pore, then the other large particle cannot pass through the pore, and the leakage came through in this case to that. So the conclusion for this is basically more layers in the membrane give a better performance, and that's basically is the big the end. Yep. And then we also have the continuum models, which basically built based on the first this first equation. Reaction advection diffusions, and where C is represent the concentration of particles in the fluid, and U is the Darcy velocity. The porosity is decreases proportional to the clogging, which is the S term, represented by the S term here. And the Darcy velocity relate the flux and the pressure gradient with the permeability and the viscosity. And we assume the fluid is incompressible, so we have the last equation. We calculate the Planck number to be small, large, but the inverse. So it indicates that the diffusion is negligible. So we take the diffusion term out, and we have the final system in our equations where all of the terms are defined here. And the S in this case represent the sticking, the rate that the particles are sticking to the pore. So it's proportional to the concentration of particles. So we simply take this to be the form of S in this case, and a table of parameters for that provided by Gore, and some calculation and guess. So we non-dimensionalize our equations, and we obtain these terms. The Chris and the Linda are constant, and these equations, where the Chris constant is about 100 times larger than the Linda constant. So, so the Linda constant help us get rid of that ugly term for our we finally arrive at this equation, which subtract to these initial conditions and these conditions. And we know that since we impose that C is basically a constant, we have a constant concentration at the top of the filter. This equation is saying that the pore radius on top of the filter is getting linearly smaller, and which basically means this equation can be just the time that it takes for the pore to get clogged can just be calculated using this equation, and that could be a problem, which we would address later. So in practice, we can either keep a constant flux or a constant pressures. And in the case of constant flux, we can basically solve for the porosity, and then we have to numerically solve for the pressure equation, which is this one. What happened? Yes. But we sort of ignore this part. And the constant pressure case is the more interesting case, where we have to solve the three blue equations. But we also sort of ignore this part. And we ended up with this equation, which basically is a modification of the previous. We're adding both the stickiness and the blocking to be the mechanisms of S. And the factor that you see here represent the geometry of the filters, where the radius, surface area, and volume. And so we have this not really nice equations where we have to solve them numerically. And solving this numerically with a constant initial porosity profile, which is this line right here, the red line that goes straight up in the middle. So over time, this red line, no. So over time, this time is proceeding this way. So the porosity is getting smaller and is clogged on the top. And similarly in this case, which is the concentrations, the initial one is the red line, and time proceeds this way. So it's also show that the concentration is, the porosity is basically being clogged at the top, and yep. So we try to vary the initial porosity profile. So we have the first layer, and then a jump to the second layer. And time proceeding this way, and this is the final porosity on the left. And it also shows that the porosity is being clogged at the top. However, in this case, there are also some clogging at the near sort of where the two layer jumps, and so it indicates that it's slightly better, and similarly for the concentrations. So we also have an alternative system where the equation is taken out. The original equation is taken from Stephen's book from chapter 10, but then they modify and get rid of the diffusion constant, the diffusion term. Then their model is a little bit different, where they keep the porosity constant but vary the pore size. So for the first one, they have the same pore size, and basically they show the same thing, that the filter is being clogged at the top. Right here. By the way, their scale is backward to, well, the correct is from 0 to 1 instead of our previous one was from 1 to 0. And for the two layer, this really hard to see, but what it's basically saying is that there is an optimization problem hidden in here that we need to address, which could be interesting for the Gore people. And we also have a cake model, which is different from the cake formations. The structure and this is a technical problem that happens in the communications. But the key is that we vary this part of the porosity up from 0.1 to 0.5, and similarly over here. And we have the throughput going, which is the higher line here, and it increases with the varying porosity in the middle. And similar over here, we also have both the throughput and the concentration increases. But if you know that the concentration, which is the line, this line here, the concentration on this figure is better because there is a 10 to the negative 3, which by the concentration at the end of the filter. So you want you want this concentration to be as small as possible, whereas over here you have a really large concentration, but the porosity, so it's not as good. And there's also an optimization problem lies in here, where you want to find the porosity that connected to layers and good alpha, where alpha represents the stickiness of the particles to the pore walls due to the chemistry. And we developed 3 models, and we got some interesting numbers, and we got some optimization problems that need to be solved for the next year. And future work, great. Yes. And we want to thank Gore, NJIT, and NSF. Thank you. Yes. Also, I will ask the audience to answer.
So if you have different modes that could be blocked, and so then it seemed like you were adding up resistances, if I understood correctly, would it make more sense to say every mode of transport has a conductance and a shut-off conductances as those modes are blocked?
That's a complicated question, and I will refer that to Pac-Man.
So basically, when we consider we have, let's say, blocking, absorption and blocking by big particles, we don't consider that the blocking by big particles happen completely, in the sense that the particle comes and sit on top of the pore, and still we have leakage underneath. So even the pore is blocked by big particles, we can still have absorption over there. That's why we are adding them to the. And also, we didn't consider cake here. Cake was studied in a lot of literatures, not a lot, but quite a lot. But the point is that people in industry, I guess, they don't like that mode, in a sense when the filter is clogged, almost clogged, they prefer to throw it away and change and get a new one.
Great. Any more questions? Yes. Which way?
My question is about the local and global network model that you had. Is it physically induced that you have a single node that connects two layers together? Is it a physical consideration that made that assumption, or is just for the simplicity that you make just one node connecting the layers?
Well, you can think about it in 2 ways. The local network that we did, you can think about it as being 2 filters, right? One being coarse, one being finer, that are as flush as it can be. They're pressed right up against each other, and there's no room for movement. The global network you can think about as not being completely flush and having a gap in between. So the particles come down through the first filter. There's a gap for room for movement. So once they go through that transfer, they have a possibility of going way down to the other side of the filter and going down another hole.
So it came from some physical cases.
That's the physical interpretation.
Okay, thank you.
The only downside to that model is it's kind of incomplete. Is what we need to add is a distribution. An additional distribution for probability of where that particle entered. Because if it enters in at a certain spot, it's less likely it's going to come way over here than close by.
So if there's no further questions, then do we have a Gore representative here who, yep, we do, who would like to.
Thank you. So first, I want to thank to the MPI committees to organize a great study group this week. As Gore, as a company, we have been benefit a lot from this workshop the past few years. For the problems, I want to thank all the faculties and the student. They're doing a great job. And for example, for the first network model, we have some great coding, and then they kind of deliver this the code for the 2-layer network, which we can use definitely later on. And then they also study this local and global network, which is kind of one of the questions we're bringing it on, because we're not sure if we implement it in different way, if there's a different result. They kind of answer that question a little bit. Also, for the continuous group, we have a great model. There are a lot of possibility to kind of extend that to some great interest problems. So overall, I hope all of you have great time this week, and thank you very much.